Generics are like a placeholder for another type. So if you think of, say, something like a can of food, and the can is always the same, but you can put different types of food in it. Those different types of food or those different contents, maybe it's soup, maybe it's corn or beans, those type of things are the generic. If you've already been following along in the previous videos, we've already been using generics with something like option or result. So in this video, we're going to talk about how to use generics with functions and with methods, and then also with your custom types, so structs. Along the way, we'll also be exploring what traits are, and we can't talk about generics without also talking about lifetimes. So we're going to get into that as well. My name is Ricky, and welcome to the Dev Method. All right, so today we're talking about removing duplication. So let's start with talking about removing duplication by trying to make our code a little bit more modular or reusable. So let me show you the first example. So this example here, we just have a vector of numbers, and we're trying to find the largest. So this is a typical like max algorithm. So we're having this largest variable be mutable, and we're just going to keep looking at every single number in the vector, and if we find something that is the new largest number, we're going to store it inside this variable largest. So that's what this does here. The comparison is done on line 28. So as your program grows, you're going to see that we have not only the number list listed here twice, but that we might need to find the largest number in two different lists. That would require us to then rewrite some of these definitions of the variables, do the same for loop again, and remember all those little intricacies about the actual algorithm. So this is exactly why functions exist, and so let's break it out into its own function. So here we have largest. Now the thing with the function here that we didn't necessarily need to do before is that we're defining what its signature is, and we're saying that it has to be something that carries an I32, and then we're going to return the I32. So this is great. This will work for I32, and if you take a look at this example and we run it, we'll find the right answers just as we did before. But now the code is kind of shrunken a little bit inside the main, and we have this for loop only actually written once, but we're using it twice. So now let's just go a little bit further, and let's say we want to use this largest algorithm, this function, but not just with integers, but also with a char type. So here now on the screen, I have the largest I32, and then I have a largest char. So you can imagine after a while, this will actually end up duplicating. Like what if we wanted like the largest string or the largest custom data type? All right, so here I go. I'm going to paste in the generic version so you can see it. There it is. All right, cool. Let's talk about the syntax real quick so you guys get an idea of what this means. So here's largest, and with that function name, after it, we have this open angle bracket, and then we have a letter T, and then close angle bracket. The letter T could be something like element as well. That is up to you. Typically, T just means some placeholder type. And then we can use it in all of the different type definitions thereafter. So here it is in the parameter of where it's called list. We're saying it's some sort of collection with T, and then we have here T as well as the return type. So now we can use this with chars, and we can use this with I32s. So pretty much most of the things there, right? That should work. So just to double check our work, let's go ahead and do a cargo run and see what happens. Okay, so we do have some errors here. And what it's actually telling us is that it wants to help us by saying consider restricting the type of T. So technically, T, just knowing that it's just some generic type is actually not enough. It's saying we should use the standard libraries compare module, and there's a type here, partial order, or ORD. And all that's saying is that line 26 here that I'm highlighting, when we're using that greater than or less than, those comparisons, Rust needs at least enough information to know how to compare them and how they're implemented for custom data types. So like I32 probably already has that built in, but when you create your own custom data types and try and use them in largest, we need a way to compare them. So they're going to have to use this partial ORD. Partial ORD is actually a trait. So this is a collection of behaviors that we can tell Rust that our types have. So if we were to create a new type and we said, hey, partial ord is something that we conform to or that we implement, then largest is going to know how to actually use this and what functions to call behind the scenes so that we can get the right behavior every single time that we pass in something that implements partial ord. So that leads us to the next part, which is using generics not only just in functions, but in your type definitions. So let's create something. Line 22 here has a struct called point. And again, we're using T. It didn't have to be T, but we're using it in this case. And then I have some examples here written in the main function. So here we're doing a point, and then these T's are actually type integers. These are defaulted to I32. But then these are defaulted to F64 floating point numbers. So that's that next one here on line 31. So you can see point actually kind of takes on slightly different identities, or you could say like a different characteristic. But essentially what we're saying is we're going to let you as the implementer using point define what the types are. Now here's the last one here where we're trying to mix types. This is important because T is replicated for X and Y, which means they have to be the same type. And that's what line 33 is actually telling us. Now if we do want them to be okay, and we want to make this totally fine, we would actually add a second type. And we could do that with separating it with a comma. So now we have a T and we have a U. U might also be used as a convention as well, just because the shape of the U looks slightly different than the T. So if you're scanning the code very quickly, it's easy to find. Sometimes you might want to give this a more descriptive name, but you'll see I'll use T and U. So here's our other types that I was talking about earlier that actually use generics. So here's the enum type. So just like structs, enums can have them. And it's got T. And then there's the two variants. So we have some, and then it's going to pass in the T. But if there's none, it doesn't pass in anything because we don't know what that would be. Result is slightly different. It actually uses two of them. So here they're actually using E for error. So this is slightly more descriptive, but you know, it's fine. And then there's T for the OK. So yeah, these are our two that have been built into the standard library that you guys can follow as examples. And now you know how to make some of your own for either structs or for enums. All right, so now we have a little bit more to unpack because we want to use generics inside of methods. So let's take a look at point again. So here in line 22, I've got point. We're just going to have it be the same type for both. And let's say we want to like get X. Because see, struct here, struct might be public. So we can mark it with pub here. But X we can't get. So if we wanted to make a function for it, we could maybe make some sort of accessor like X, give me X from self. And what this would do is let us get X here. That's the idea. That's the whole point of what we're getting at here. But because we have generics inside of our points, we're going to have to then specify them again in the implementation. So as we're making our method, we use impl just like we did before, but then we have to specify the generic here and then put that generic also inside of point. So we have here X, and X we want to, this is a method. We want to actually pass the value back of X, but as a reference. So that's what this is going to help us accomplish. Now, no matter what T actually is, we're always passing it back as a reference. That's what this signature and that's what this method is meant to do. If we want to be more specific, we can actually target a specific type of point. So if we ever make point a float 32, it's going to have now this special method introduced to it. And then that way we can use the F32 because we know that that's what we're dealing with when we're dealing with X and Y now. So we could use these different methods just for specific types. So it's completely up to you how you want to do that. All right, so the next example, we're going to actually mix some of these types here. So let's take a look at struct again on line 22, the point struct. And we're using this X1 and Y1. Okay, I just want you to pay attention to that. Now, here's the thing. The implementation of this, we're going to have a method called mixup. And if you look on line 40, this is where we use it here. We're going to take one point, call mixup on it, and it's going to return, we're going to give it a second point, and then it's going to return this like third point. So on line 28, here's the definition of mixup. Now, here's the thing. We have X2 and Y2 as generic parameters just to this method. So we're like mixing up the types here, and the idea is that we're going to take the x from the first one and then the y from the other one, or the thing that we passed in. So we're going to ignore what x2 actually is in the output. So notice that's why y2 is in the return type for point, and x1 is the return type in there as well. So it's just showing an example of how to mix some of these things up. So for example, in P2, on line 38 here, we have P2. Instead of the integer with float, now we have like a string with char. And if we mix them up, that means we're going to take this first one. So we're going to take an integer. This is going to be an integer then. And then y, it's going to be the character. So essentially what we're kind of making here is this. Something with an I32 and a character. So that's the idea. So let's talk about performance for a second. We're sacrificing the performance on the compiler side because the compiler has to do a little bit more work. And then we're actually growing our binary just a little bit when we're using generics, and we use them for many different types. So if I had the largest function and I used it for the float, I used it for an integer, so we'll actually have two implementations of that function. One's going to be for the I32, and the other one's going to be for the F64. So the word we're looking for here that you'll find in the Rust programming book is monomorphization. So monomorphization is the process of turning generic code into specific code by filling in the concrete types used at compile time. So here's our example. Let's say we have an option that we're using, and it's integer, right? So this would be an I32, and here we've given it a value. And this is the part that's in our code. We have an integer version, and then we have a float. That's the idea. So monomorphization, I'll say that 10 times fast, that is what's happening here on the code below. We actually get an enum as an I32, and then we get an enum as a F64, both of option. That's the idea. So this code used is what is actually put in by the compiler, what's in main here. So it would have been what line 22 and 23 are, written in your code, but then the compiler is essentially outputting something just like this. All right, let's move on and let's talk about traits. I already got the example up here. So I have a summary trait here, and I have this thing called summarize. So that's going to be a method on whatever our type is that's going to implement it, and it's going to return a string. So I have our own news article here, our custom data type. It's got a headline, location, author, content. So now we implement summary, right? Now that means that's the trait. And then we use for our custom data type, which is news article. So that's how that works. And here I'm filling in that implementation real quick, just by doing some formatting string, using the format macro in Rust. The headline, the author, and the location. It's got a little bit of something in there, just so you can see the differences there. Now let's look at another one. Here's for tweet. Here's our custom data type there. We have summary, again, which is the implementation block for summary, for the custom data type, which is a tweet. And then notice that that implementation is slightly different. We are using the same function, but really the possibilities are endless. Whatever you're putting in the implementation of summarize, it's going to be different for all of these custom data types. All right, so now I have an example of using them. So here I got the tweet, and then we're going to print out the tweet. Let's run this just so you see the difference. All right, so here it is. It says horses, book, ebooks, of course, as you probably already know, people. So that's just saying the one tweet there. All right, so here's the idea. We said that it was a pub trait, so a public trait. So the idea with summary is that it's now can be used in other modules. So if I bring it into my application or my module and I want to use it, it's like an external trait that's been defined elsewhere, and now I can use it on my own custom data types that I define in that module. The one thing you couldn't do would be take in summary and then now have something from another external module that doesn't import summary and have them implement a custom implementation for summarize. That just doesn't work. Let's extend summary a little bit. So here we have summarize author as a method, just like how we had before with summarize, but now we're just saying just the author. It has no definition, just like before. But now, on line 27, we have summarize, and we're giving it a default implementation. So the tweet struct that we had from before, it wouldn't need to be updated because all we would need to do is update the summarize author part. And we've already put in summarize author here for news article on line 34. But summarize for both of them wouldn't need to be implemented because I already have a default implementation. So next here in this example, we're going to use traits as parameters into functions. So here we have notify. And all we're doing is we're giving it an item. Now that item, the type of it, is going to be a reference to something that implements summary. So this could be our news article or a tweet that we've used before. But that's the idea. That's what that's going for. If we want it to be a little bit more verbose, just expand it a little bit more. This is another way to write the same exact thing. Instead we're saying like we have something of type T. We're using those generics again. But it implements summary, the summary trait, and then here we are using it as a reference. So that's the idea. Now we also could use it with two items like this, like if notify had item 1 and item 2, then we also have an example of breaking that down for just item 1 and item 2, but now with the generic form. Now another thing you could do too, since we're using these generic types with traits, is that we can actually say you have to implement 1 to 2 or more different traits and then also use that as a parameter in your function. So the example here is we have notify, again, with the item, but now we're saying something that implements summary and display, the thing that it gives you like the to string. So that right here is separated by a plus. And then here's like the more verbose form with the generics added in there. This is what that looks like. Very similar, but just slightly different, but no difference when you actually use it in your code. This is just the idea. So it could also be said that there's another way to expand this even further to maybe make it more clear. So you're starting to add many different conformances for your generics. So here I have some function on line 24. We have the generic type T, which will implement display and clone, and then I have a generic type U that also implements implements clone and debug. So slightly different, and that's why we have those two types. So one's passed in as the parameter T and then U accordingly. And then in the end, it's going to just return us an I32. So that's one way to do it. But if we want to declare it maybe in a slightly easier readable format, that would be 27. So we have T and U. We use T and U as the parameters. And then we say the return type. But then after that, now you don't have to put it on the separate line. But here it's just made to look a little bit nicer for us to read. We have where, and then T is going to then have the display and clone, and U is going to have clone and debug. So these are both equivalent. You can write them whichever way you want. One is arguably cleaner than the other, but that's just what the Rust programming book tells us. So it's up to you to decide. So another thing that we have here, if you take a look at this example, we're going to use the summary, the trait, but as a return type now. So we have here line 24, return summarizable, and we're just giving it some sort of tweet, right? But we don't know which kind it is, and that's where we return something that implements summary. So that's pretty cool. So let's expand this implementation just a little bit because we have tweet and we have news article. So let's say the implementation, if we look on line 25, we have a switch here. And depending on whether that's true or false, we're going to get a news article or we're going to get a tweet. Now, the code that you might write is not always as straightforward as this, but the idea is the same. You're going to return different concrete types based on some sort of business logic inside of your function. So here, if we're looking at it, we have we're returning summary, but it could be a news article or it could be a tweet. And actually, Rust doesn't let us do this. They all have to be the same type. We're not ready to really talk about the solution for this problem, but it is covered in Chapter 17 of the Rust programming book. However, let me give you a sneak peek with my own little twist of an example. So here's that summary trait. And then we have the trait Ricky, or the struct Ricky that implements summary. We have arc that implements summary. And then we have that flag, same as we had before. You can use something here, a box, and use this dyn, which is a dynamic type for summary. Essentially using something very similar, or if not equivalent, to dynamic dispatch. So again, look in the Rust programming book, Chapter 17, if you want to learn more. So now let's go all the way back to the beginning and look at the largest function, and let's add those fixes that we now know how to fix. So one of them was the partial part. The other one we didn't really get into, but we would have eventually gotten into, was this idea of a copy. So instead of returning a reference, we want to return just the value itself. So that's where we need to know that this item that we're passing in can also be copyable or cloned. So that's here, largest. Copy trait is this part here. So this is saying for every item, can we take it out and use it to compare against whatever we think is the largest. So that's the part there that we didn't know before, but now we do because we're using generics. So now we know how to use this largest function, and we have the generic t that has to implement not just one, but two different traits. Lifetimes are another kind of generic in Rust. We've actually already been using them and we didn't even know it because you don't always have to specify them in your code. So lifetimes are a little bit more about the validation of the scope of the variables that you're passing in. How long do they live for, and do they live long enough to be read or written to or still be valid to operate with? So let's review scopes again real quick. I have an example here, and this is an example that would fail. It would not pass the Rust compiler. But let's take a look at this idea of this single quote A or a tick A. That's kind of the idea when we're using lifetimes. So that's what we're going to use here. So we have R, and then we make a brand new scope, and we want to reference R, and we want to give it X. And we're giving it a reference to X in R. So now we know what the type is. It's a reference to an I32. That's because of the 5 that's implemented here or written with the X. So B only lasts for this little scope here. At line 30, X gets dropped. Now, if we have a reference to X, that's a bad thing because now that's like a dangling pointer. So it got dropped, but here we are trying to reference it again when we use the print line for R. So that's a bad thing. So lifetimes are very much a tool to get rid of dangling pointers. And as you might have guessed, this is an example here, looking at line 25, where we're fixing the problems we had before. We actually took B and moved that up in this line order, and we got rid of that block scope there. And then we're referencing it to R, so now we have A, and now we can read R into println, and we're all good. Everything's validated, totally fine with the Rust compiler. So let's go back to something similar to the largest function here. We're calling it longest, and let's see if lifetimes apply to it. So here we're finding that we have X and Y, which are both strings, and then we're going to return the string that is the longest out of the two. That's the idea. So here we have line 31 and then line 32, two different strings, pass it into longest, which is the result, and we should get something, right? So let's run this and make sure it works. Aha. So expected lifetime parameter. So it's already telling us in the Rust compiler, because it's really smart, it's helping us. So this function's return type contains a borrowed value, and they're talking about the reference there. But the signature does not say whether it is borrowed from X or from Y. And conditionally in the logic, it could be from X or Y. We just won't know until runtime. So consider introducing lifetime parameters. And here they're actually showing us exactly what we would want to add. So now I've added them in, just like how it said in this error message here. And let's try and run it again. All right, cool, it worked. So let's take a look at how this lifetime reference stuff works. We have here a reference to I32, something we've known before. But now introducing the lifetime syntax, it's going to be a reference and then that tick or that single quote, A, space, and then that underlying type here. So this is a reference with an explicit lifetime. All right, so let's take an example here with longest. This example on line 36 is where we're using it. And so if we look at string 1 and where that comes from, line 31, and then string 2 in this different scope, but within line 34, does this work? Well, let's see if the Rust compiler tells us so. Yep, it does work. And we know this because result and string 2 and string 1 all have the same lifetime. They live for as long as it takes to the last usage of result. So that works. That's how we know that that is working with our lifetimes. But now what if we did this? We put result up here. Would that work? Is that the same thing? Let's see. Yep, that works. Now let's say we put the println outside this inner block. Now does that work? Aha, it doesn't. So string 2 does not live long enough. It is a borrowed value. Let's take a look here up above. Yeah, so string 2 gets dropped at this point. But we have guaranteed in the signature of longest that this value lives just as long as 2 does. And in this case, we know it doesn't because we are borrowing it later to be put into println. String 2 was dropped here while still borrowed. So there we go. Rust is helping us out. So here on line 25, let's talk about something. We have the input lifetimes, which are the parameters, and then we have something called the output lifetimes. And so the lifetimes are really helping us connect these parameters we're passing in to also then the return values. So y is never returned, so the function doesn't need its signature. So here you can see y doesn't have a lifetime, but x does because we're actually using x in the return type as well. So that's why we would need it. Now, on the next one here, this longest, this actually gives a dingling pointer. So if we wanted to return result, but as a string, the result gets dropped and therefore it's like cleaned up. So whatever it was returning, which was also some sort of borrowed type as str, that doesn't work because it doesn't live as long as we need it to. So that's cleaning up that dingling pointer reference. So lifetimes don't just go in your function parameters, but they also go into your structs. So here I have an example. It's an important excerpt. So like if you're reading a novel and there's like this little tangent thing that you need to also read about, that's where we have this excerpt here. Now the excerpt, we actually have a part of it, and that's the property. Now part is actually given a lifetime as well. So for the excerpt, for as long as the excerpt lives, we also need the part to live, and that's because we're using that reference. So whatever the reference is that we get, we need to make sure excerpt also lives for the same amount of time as that reference. So here in line 27, we create the novel, we get the first sentence. That seems all just regular Rust code, but now here, an instance of excerpt cannot outlive the reference that it holds. So here, first sentence, it comes from novel, so it's like owned by novel. And now we have the excerpt itself, which is just right here in I. So both the novel and I need to have the same lifetime. So they need to be in scope and valid for the same amount of time. And they are here in this case, so this works. So here's another function signature. It's called first word. So you give it a string, and we're going to turn the first word also as a string. So here we're kind of maybe already seeing that we need these lifetimes. In earlier versions of Rust, we might needed to have actually explicitly annotate these lifetimes. But here we actually don't need to. So this will actually compile and this will run, and that's fine. So what we're saying here is that S will have the same lifetime as the return type because we're borrowing something in S and then returning it as a reference. So both need to live the same amount of time, and Rust is actually able to figure this out for us. The reason we can do this is that the borrow checker inside of Rust recognizes these patterns, and there's a couple of rules that the borrow checker and the compiler follow to see if it can insert the lifetimes for you at compile time. It doesn't always work. Sometimes it's a little bit ambiguous to the compiler, so you as the developer need to insert them yourselves so that you can be very explicit about what it is that you mean. Now we call these rules, but they're not like hard rules that you as a developer need to follow. It's just something that the compiler does. So it might be interesting to understand what these rules are that are being followed. So here's the first rule. The compiler assigns a lifetime value to each parameter that is a reference. So in these two examples, we have X, so the compiler automatically put in, since it's a reference to an I32, already put them in. Now here on line 23, we have two parameters that are passed in for this function, and each one of them get their own individual lifetime. They are not shared. So that's where the A and the B come from. And then so we have the reference and then the A lifetime, and then we have the reference and the B lifetime on both X and Y accordingly. So the second rule that we have is that there's exactly one input lifetime parameter, then there's a lifetime parameter assigned to all of the output. So for example, we have here on line 49, we have A, because there's only one parameter that's an input parameter. That means the output parameter also gets the same lifetime as that. And again, these are both because they are references. And then the third rule for the elision is that if there are multiple input lifetime parameters, but one of them is a reference to self or reference to mutable self, and that is because it's a method, the lifetime of self is assigned to all the output lifetime parameters. So we'll see an example of that in the coming example. So here's our first example, and we'll go line by line as it evolves with the different elision rules. So 94 is how it's written. I've got first word here, and it has a parameter reference to a string, and then outputs a reference to a string. So what we would have to do, since it has that first elision rule, it is given its own lifetime because it's a parameter. Now the second elision rule says that if there's exactly one parameter that has that lifetime, then the output also has that same lifetime. So here it is. That's what we have there. Now after that, for this method signature or this function signature, we're actually all done. The compiler has done the elision rules for us, and we're good to go. Now with this second example, we have here the two parameters, okay, and then we have the output, and they're all references here. So each one is given their own lifetime, right? Because there's two parameters. That's part of elision rule 1. Now the thing is, rule 2 does not apply because there are multiple parameters. Now here's the thing, rule 3 doesn't apply because there's no method, so there's no reference to self. However, because of what we have written here, that we have two different parameters, we actually don't know what the lifetime is for the output. So us as the human would have to insert that into the application. So in this case, I mean, maybe we put them both as A, and then this one's going to have A as well. Really just depends on what it is that your function is trying to do. So let's take a look at the elision rules, but with a method. So here we have the important excerpt again from our novel. And here's an implementation for it, right? So we have a lifetime already specified. So the part here, this property, has that same lifetime that's been specified. So let's skip down here to line 127. We have here announce and return part. So each one of these steps is going to be our look into like how the compiler is figuring this out for us with the elision rules. So on 127 is what we have written. And let's see how elision then works into this. So the first elision rule, each parameter gets their own lifetime. So we have the two parameters, so self is going to get one. And then announcement, that parameter gets one as well. Now, since there is more than one parameter, we're going to skip the second rule. Now, on the last one, since we are dealing with a method, the rule does then apply. So if we have self here, that means the return type also has to have the same lifetime as self. So in this case, if this is what we have, this is how it works automatically. That means part is going to have the same lifetime as what self is, and that actually is true even based up here on the method signature itself. So that checks out, that works. All right, so one of the compiler checks that you might find when running your build on your cargo project, we have here S, and you might get suggested to make it a static lifetime, because static is actually really specific to some sort of variable or something that needs to be around for the entirety of the application running. So something like this global S variable, which might stay around forever, at least while the program's executing, that gets the static. So that's like a special type of lifetime that you can give your variables. Now, one thing to note, just a warning, if the compiler references static and you're not really sure if it should, because it's not a global variable like this, then you should relook at the lifetimes of some of the functions you're already using within that piece of code to figure out maybe one of those things needs to be adjusted or fixed. All right, now this example, we're going to mix all of them together, the traits, the generics, the lifetimes. So here on line 200, we have longest with an announcement, and we actually have 3 parameters here. The first and the second parameter have that lifetime, so that's what's specified in the angle brackets here. Now we have T though, so that's like the announcement, the ANN, and then that's just given there as the type. Now the thing with T is that it actually implements or is required to implement display. That way we can use it in println here, and we can just use it in like this format string. But then these lifetime parameters are very similar to like the longest here. We don't know if we're returning X or Y, but one of them is going to be returned. So that's what we're doing here with the A in the return type. So there's all of them together. So if you want to learn more, again, chapter 17 of the Rust programming book is going to have this. And I'll also put a link in the description for the Rust reference There's a couple of more like expert or advanced scenarios. You might want to use lifetimes and these traits and stuff. So I'll put that in the description so you can read it. If you guys like the video, go ahead and give it a thumbs up and subscribe if you want to see more like this in the future. And if you haven't already, I am on Twitter at @thedevmethod. That way you guys can see updates about when I upload new videos or if I have commentary from them. All right, otherwise, have a good one.